All right, welcome everyone. This lecture's it's actually in two parts. There's one on kinetics and there's one on equilibria. So as you can see here, the first bit's on kinetics. Just before I start this, just to give you an idea on what's happening here, basically I'm trying to answer two questions here. One is you're talking about reactions and you're asking the question, how fast are those reactions going? And that's kinetics. And the other one is, the other question is how far are reactions going? And that's to do with equilibria, which we see in the second part of this lecture. So just be aware of that as you're going through this. We're actually trying to look at two different questions here. One is how fast, this one, and then the other one is how far, the second one. Okay. Okay, so now clearly if I'm talking about how fast reactions are occurring, there's got to be some way of measuring them. So before we even get into this in any great detail, we've just got to take a little back step for a moment and just think about how you actually measure the rates of things. And the bottom line is for anything when you're measuring the rate, it's going to be something per unit time, so per hour, per second, per minute, etc. I just thought I'd start with this example here, something we're a little bit more familiar with as far as rates go. What I've done here is I've plotted the distance that you've covered or we've covered over time, or I've covered over time um, for a journey from, say, the Sunshine Coast to Brisbane. So at some point here, right at the beginning, time zero, let's get our pen here, at time zero, obviously we haven't moved yet, and so therefore the distance we've traveled is zero, the time is zero, so we're sitting right there. Now as you drive off, of course you're driving through the suburbs. Sometimes if you're lucky you don't get any traffic lights, and and your speed is constant. Let's say it's at 40 kilometers an hour. Whatever it is, if you're then plotting the distance you're covering over time, you'll get something like this, where it's a straight line here. And by measuring the distance that you've covered, that's the distance there that you've covered between that point and that point. There's your distance that you've covered, and you divide that by the time, that's that point and that point. You can calculate your speed, which is a rate, basically. It's the change in distance over the change in time. Now, just as a little reminder, these little delta signs here means change in, so change in distance, change in time. And for a straight line, I think it's pretty straightforward, right? And it doesn't matter which time point you pick here when it's a straight line. You could have picked here, in which case the distance will be less, but so will the time. So the numbers will square up the same. They'll be the same speed. Now let's say if I'm lucky and I don't get any traffic lights and I basically get onto the motorway. And of course, when I'm on the motorway, my speed is going to increase. Let's say it more or less happens very quickly here. And I've now got a constant speed here, as you can see, and that constant speed, it could be 100 kilometers per hour, for example. You can see the slope of the line is a lot steeper than what it is here. And if you were again to figure out what the speed is, that is the rate at which you're traveling or covering distance per unit time, you would simply take some arbitrary point there, and then measure the change in distance over, again, the change in time here. There it is, and then you can, of course, calculate your speed. And again, same argument applies. It doesn't matter where you pick. You'll always be able to do that. So that's all good when the rate is constant, but what happens if the rate changes? Well, I've drawn an example here where the rate's changing now. So it's a little bit more difficult to figure out what your speed is because there's no straight line here, there's no slope of a line. But what you can do is you can draw what's called a tangent to the line or the curve here, and it's just where it just kisses it. And when you draw that tangent, you again get, as you can see here, a straight line. And then of course you're back to being able to measure the change in distance over time. And of course then you can measure the rate. Now the rate changes depending on where you are in relation to this curve here, and of course you would get a different tangent. So the tangent to this part here is more along that way, and then it starts, as you can see, going up like this, and then it's steeper here, of course, etc. So you can actually measure the rates for a curve or a line that's not linear, but you have to draw a tangent to the curve, and then you find the slope of the tangent. Now, I want you to keep that in mind because that's what we're going to be doing with these chemical reactions. By the way, you might have learned this before, as when you're measuring these slopes here, as rise, in this case it would be distance, over run, in this case it would be time. Either way, the principle obviously is the same. Okay, so now we're going to get on, now that we've got the basic idea of how to measure rates, let's have a look at what happens when we're considering a formula. So in this case here, I've picked this example where we've got, or I shouldn't say just a formula, a chemical reaction here where I've got ammonia and it's decomposing, reacting to form N2, nitrogen gas, and H2. And the equation is balanced. As you can see here, the number of hydrogens on both sides is the same, and the number of nitrogens on both sides is the same. So that's all good as well. So we're gonna look at how you would actually measure the rate of this reaction here, and clearly it's going to be a change in something per unit time. Now, I know this looks horribly messy, but it's not as bad as you think. What we've done here is, let's just start with the axes here. There's our time component, just like before, the one I showed you with the trip to Brisbane. In this case, it's in seconds. And we've got intervals here at 0, 500, 1000 seconds, etc. The difference, of course, because it's a chemical reaction, is that it's not distance this time that we're measuring the change in, it's actually the concentration. So if you recall, many times in chemistry when we're measuring concentration, we use molarity. So this concentration is in molar here. So this would be 1 by 10 to the minus 3 molar, 2 by 10 to the minus 3 molar, etc. So we've got concentration here, time here, and when you carry out the reaction, this is the sort of thing that you get. So let me just pick this apart for you because it looks awfully messy to start with. So we're going to start at time 0. At time 0 here, these two lines are at 0, and if we read up here, you'll see this line is referring to H2, right? So there's hydrogen there, and there you can see there's nitrogen there. So they're the two products. And so you would expect at time 0, there's no product present at all. Obviously, you have to start off with some amount of reactant, and in this case, the amount of reactant we're starting with, and the reactant, of course, is ammonia, is this much here, right, which is a smidgen under 3 by 10 to the minus 3 molar. Now, before we follow this through, let's just think about this. I mean, obviously, if the ammonia is reacting, its concentration must be going down, which you can see here. It's going down this way. And of course, as it's reacting, it's now producing N2 and H2. I got those around the wrong way, but you know what I mean. There's N2, there's H2 going up in that direction. So that's the data. Okay, now let's try and make some sense of this data. Well, the first thing you'll notice is that none of these three curves are straight lines. They're all curved lines, and so therefore if we want to find the rate And by the way, that the term that you would use to find the rate at a particular point is called the instantaneous rate. So if you want to find the rate at any point, obviously you have to draw a tangent to the curve. So if we look at ammonia here, so what I'm going to do actually is I can use this one. If we look at let's get that pen back again. If we look at ammonia here as it's going down, for this example, they've chosen this 500-second mark as the arbitrary time point there. So they've drawn a tangent to the curve at that point there. And then what they've done is they found the slope of the line. Now the slope is this bit here, and it's rise over run. But because the ammonia concentration's going down, they've said, well, okay, it's a decrease, and so therefore we're going to make it negative here. So they've found that the rate at which the ammonia is decomposing is 1.94 by 10 to the minus 6 molar per second. Okay, and then what they've done is at the same time point here at 500, they've taken tangents to the curve for the hydrogen and for the nitrogen here, and they've also calculated the slopes of those tangents to the curves. So what does all this mean? Well, basically each time point is unique. It's called, and you're talking here about at any particular point, there's an instantaneous rate here, and the thing that's most important is this. If we go back here and look at this equation, hopefully you can see that for every 2 ammonia that decompose, you only produce 1 N2. So it's actually the amount of N2 is being produced at half the rate. And if you look here in the camera for a sec, there's my fingers. So it's 2, goes backwards in mirror form, 2 ammonia produce 1 N2. 2 ammonia, 1 N2, like that. So you would think that the N2 production here would be going up at half the rate that the ammonia is actually decreasing. And that's actually the case, because if you look at the amount of N2, it's this amount. That's the rate there that it's actually going up. And if you look at the amount of NH3, it's this amount. Now, those numbers are a little bit confusing to square up, because this is down here, this one's 10 to the minus 7 and this is 10 to the minus 6. But if I wrote this number as 10 to the minus 7, that's actually 19.4 by 10 to the minus 7, so it's easier to compare here. So I'm comparing 19.4 to 9.7, and you can see it's actually twice the rate. In other words, the ammonia is decreasing at twice the rate that the N2 is going up. And if you look at the hydrogen, when you compare the excuse me, when you compare the hydrogen here to the ammonia, you would expect that the hydrogen actually goes up at 3 on 2. In other words, 1.5 times the rate that the ammonia will decompose, and that's the case there, right? Because 1.5 times 1.94 is about 2.91. So it's about 2, that's about 3, it's about 1.5 times. Okay, so let's just go over here and look at these dot points to make sure that I've covered everything. Basically here what we're doing is we're trying to measure the rate of the reaction. The rate of any reaction can be measured either by the decrease in the concentration of the reactants or an increase in the products. You'll notice here that as the reaction progresses, the lines actually start to flatten out. In other words, the slopes decrease in magnitude here, the reaction slows down, and that's exactly what you would expect because you've got less and less ammonia as the reaction progresses. And of course, that means they can't, those molecules can't react as quickly, there's not as many of them. And so you would expect the rates to slow over time. I've talked about the instantaneous rate. It's the rate at any time measured as a tangent to the curve. You can see why that has to be the case. Just a couple of other clarifying points here that you may come across when you're reading. The initial rate is actually the rate at the beginning of the reaction. So that's there, tangents to the curves there. People sometimes use them quite a bit because at that point everything's kind of set exactly the way it should be for that particular rate. It's particularly used in things like enzymology when you're measuring the rates of reactions for enzyme catalyzed reactions. So just be aware of that. Rates can be averaged, but it's normally not a very good thing to do, right? Because you're basically getting an average between that over that, but it's kind of an assumption that this is close enough to a straight line, and that's not actually true in some cases. So just be aware of that. But some people do express things in terms of an average. The rates, as I mentioned before, you're looking at molar per unit time. So it's a change in concentration per unit time. And as you can see here from what I've shown you, these rates at any given time point, in this case we used 500 seconds as the example, reflect the stoichiometry of the reaction. So in other words, if this is decomposing, this has got to be produced at half the rate because the stoichiometric ratio is 2:1, and this one here would be produced at 3:2 times the rate because the stoichiometric ratio is 2:3, or 1.5 times. Okay, so again, just that point, relative rates reflect that reaction stoichiometry. There's just a little summary for you. It's basically what I've just said. Now here's an example of how this would work. You've got material here, hydrogen peroxide. It's decomposing according to this equation here. You can notice, I hope, straight away the equation's balanced. And that's reflecting the stoichiometry of the reaction, of course. And then based on the data in figure 12.3, that's actually your reference textbook, the decomposition of peroxide at 11.1 hours, that's just the point they'd picked, because of course you're going to get a line like that kind of thing, or not like that, more like that, right? So they picked some point where they've then got taken the tangent to the slope of the line there. Okay. Anyway, what is determined to be this amount? So it's 3.2 by 10 to the minus 2 moles per liter per hour, or I could have written that obviously as molar per hour. It doesn't really matter. Anyway, what is the instantaneous rate of production of water and oxygen at this time point? Well, you just simply look up here and you go, okay, well, for every 2 of these peroxides that break down, I get 2 waters. In other words, the stoichiometric ratio is 2:2, which is 1:1. So if this is the rate at that time point, which has been measured, then obviously the rate of production of water would be equal to this rate because they're precisely the same, well, they're equal stoichiometric ratios. For the oxygen, you'll notice that for every 2 of these peroxides that break down, you only get 1 oxygen. So in other words, oxygen is being produced at half the rate that peroxide is being broken down, and so therefore it would be half of this rate here for the oxygen. And that's what I've written here as the answer. Water is produced at the same rate that peroxide is consumed because the stoichiometry is the same. Therefore, the rate of water production is exactly the same as that cited up there. Whereas For oxygen, it's produced at half the rate of peroxide decomposition, and so therefore the rate is half that amount. In other words, it's 1.6 by 10 to the minus 2. Okay, we'll leave it there.